So again, let us first recall, say if we want to calculate the endpoint function in the interacting theory, and this is given by this following ratio in the free theory. Look at this t, then you look at this, again take this product to be x, take the tx exponential isi, then in the free theory, and then divide it just by time order isi in the free theory. Okay. So what we do is we just expand these two exponential in power series. Okay, we expand this exponential in power series, and so when you expand in power series, then for example the nth order term in the upstairs say upstairs then have the following structure. You have I to the power n factorial. Then you have p x, then si to the power to nsi. Okay. And the nth order for the downstairs, you can also expand the downstairs say in the downstairs, similarly, then you have almost identical structure, except you don't have this x. Okay, so you have t, then you just have n as i's. Okay, so there's n of them. So there are n of them. Okay. And the last time, so we described how to compute, say, a typical terms in here. Okay, so let me call this equation star, equation star star. So last time we described, so the star and the star star can be computed using Wick theorem. Okay, but in practice, what we do is that we first draw Feynman diagrams. And then we convert the Feynman diagrams into, say, analytic expressions. Okay. So normally we go through this procedure. Okay, rather than directly do the weak contraction. Rather than directly do the weak contraction. Okay, so we mentioned the and the second line, of course, is just can be considered as a special case of the first line, which you just with this x to be identity. Okay, with x to be identity. So any diagram contributing to star, okay, because sorry, I should actually, so here I have n, let me call it m, it's so that they don't, sorry, I should call it m so that they don't, because we already have n here, okay. So m's order, okay? So any diagram contributing to, say, the star has n external legs. Okay, has n external legs. So that comes from just from this x, okay, from this phi x1 and the phi xn, okay. And then also with m vertices, okay, because each vertices come from a power of Si, okay, a power of Si. But for star-star, so diagrams contributing to star-star have no external legs, okay, because there's no low x here, there's no phi here, okay, there's no external legs. Okay, so that's why they are all called vacuum diagrams. Okay, and they are called vacuum diagrams. Okay. So the downstairs can be understood as in the case which you just essentially take when you take x equal to 1. So essentially we are calculating the some kind of unnormalized transition just the overlap between the vacuum itself, okay, between the vacuum itself from minus infinity to plus infinity, okay, from minus infinity to plus infinity. So so in P set 6, okay, in P set 6, just in the P set we just posted last night, you can show that this quantity, which come from summing over all possible vacuum diagrams, okay, the diagrams without external legs, okay, have low, sorry, I should say have low external leg. This no is very important. Has no external legs, and so they're called vacuum diagrams. So so in P set 6 you will show yourself, okay, it's a pretty simple calculation, but it's an instructive one. You can show that this quantity can be used to calculate the vacuum energy. Okay, the vacuum energy of the interacting series. Of course, this is divergent, but just as the vacuum energy we calculated before in free series, okay. So this one can be used to calculate the vacuum energy of the interacting series. Okay. So of course this quantity will you will see it's divergent, but at least this is a formal way to calculate it, and and how to remove the divergences, etc., is something we will not discuss. Okay. In this class, will be in next class. Will be in QFT2. So, any questions on this? Okay, good. So let me say a few more words. So when we compute 2, so there we say they can be computed using the Feynman diagram. So let me be a little bit more explicit. So the computation of star or star-star say essentially involve 2 steps. So I just elaborate that remark in the bracket. Is that we first draw all possible, all inequivalent Feynman diagrams. Okay. So in this case, so at each order, at each mth order, you have n point, n external point, and then you have m vertices. Yeah, so there you have, say, for star, you just have, say, n external points, say x1, x2, say in coordinate space. You have n external points, and then you have m vertices. And at each vertices, you have, say let's call it y1, y2, ym. And each vertices, you have 4 legs coming out. Okay? And at each external point, you have one vertex come out, one line come out. Okay? And then you just need to find all possible ways to connect them. So that we mean by drawing all inequivalent diagrams. Okay, you just you just draw it. Okay, become mechanical. Become mechanical. Yes.
Why do the vertices have to all have 4 legs?
Yeah. Oh, we are talking about the. Here we are talking about the. Yeah, more specifically here we're talking about the SI. Yeah. So this is for the SI equal to minus lambda 4 factorial. We consider this particular theory. Okay. We consider. Yeah. I'm going to make remarks on other more general theories. But yeah. Here is more specific. Yeah. Other questions? Okay. So this is for star. So for star, then you just don't have the x. You just have y's. You just have my, and each y have 4 legs. You just connect all of them together. Okay, you connect all of them together. So in the star in the vacuum diagrams, so it will be always closed. Okay, because there's not no external leg, just because all the legs will be contracted, and so will be a closed diagram. Okay. And so sometimes also called the vacuum bubble. Okay, sometimes we call vacuum diagrams or vacuum bubbles. So here it's always a closed diagrams. Okay, closed diagrams. And so this is and the second step is that now once you draw all the inequivalent diagrams, then you can just convert each diagram to an algebraic expression using Feynman rules. Okay. And then you just sum all of them together. Okay, then you sum all of them together. And then we talked about the Feynman rules last time. There's a coordinate space rules. There's a momentum space rules. You can do it in coordinate space. You can do it in momentum space. So I will not repeat them here to save time. And so once we finish the second step, then you just have a bunch of analytic expressions, and then you just need to do the integrals. Okay, so a bunch of integrals, and you just need to do the integrals. Okay. Any questions? Good. So some further remarks on one. So further remarks. on this first step. So here I consider a very special case. Okay, here I consider a very special case corresponding to this SI to be just consider a single term phi 4. Okay, so in principle, of course, SI can contain multiple terms. Okay, can contain multiple terms. So then, yeah, if you contain multiple terms, then you will have multiple types of vertices. But the rule is similar. You just say if you have the say suppose SI contain two terms, and then you just multiply them. Okay, and each then you get many terms here, and yeah, just corresponding to different combinations of vertices. Okay, for different type of vertices. But the rule is exactly the same. Okay, just now your diagrams are more complicated. Okay, your diagram is more complicated, but essentially it's otherwise it's identical. So another thing to mention is that in principle we can also have multiple fields. So here we consider only a single scalar field phi, but you can also in principle consider more than one field. Okay, so if there are multiple fields. The story is again very much parallel, and the only difference is that each field, each propagator is represented by different line. Okay. Say other than that, yeah. Again, these two steps again apply. Okay. I just allow you actually have now two different type of lines. So for example, for example, if you consider a series with two scalar fields, phi 1, phi 2. Okay, with SI, say for example with SI. Say proportional to phi 1 square, phi 2 square. Okay, and then in this case, then you will have a propagator for phi 1. Then you also have a propagator for phi 2. So now I can use a dashed line. And then the interaction vertex, then we'll have the following structure. You have 2, and then you have two. Solid line and 2 dashed line. Now that's your vertex. Okay, and yeah. So yeah. Again, you just contract all possible lines according to your Feynman rules. Okay. Good. So also one remarks I want to make to emphasize is that in momentum space, yeah. So yeah, just to another point to stress. So in momentum space, so this is obtained by Fourier transform. So this is obtained by Fourier transform Gn(x1) xn. Okay. And times times the delta function. So this times this give you the Fourier transform of that. So when you do the Fourier transform, Of course, so P1 and Pn, they just come from doing Fourier transform corresponding to momentum for x1 and xn. So here the P1 and the Pn just arbitrary, okay? They don't have to be satisfy any on-shell condition. They're just arbitrary momentum. And the only constraint is that this is non-vanishing only when they are only when the sum of them are equal to 0. Otherwise, they can be arbitrary. Okay. Good. So in practice, now you have a way to calculate the diagram for both upstairs and downstairs. And now we just do the expansion. Okay, we just do the expansion. Then it's just again. Now let me summarize the example we did last time. Now just only using diagrams. Okay. So for example, if we consider 2-point function. Okay, let's consider 2-point function. So now the upstairs. So we have the upstairs and downstairs. So the upstairs, the lowest order, you just have a single line. Okay, it just have a single line x1 to x2. So to save effort, that will also not label x1, x2 from now on. Okay, and then the next order is you bring down 1 power of this Si. So you bring down 1 power of these 4 indices. So now there are 2 possibilities. Okay. So one possibility is that you still have this, but then times this vertex contracts to itself. Okay, contract itself. And then another possibility is that you have something like this. Okay, and you contract with the vertex. So this is then plus lambda squared. Okay, so this is the order to the lambda order. Okay, and downstairs you have 1, and then you just essentially have have a single SI. A single SI, the only contraction is just given by this. Okay, and then plus all the lambda square. Okay, plus all the lambda square. Okay. So now we can just. So now each vertex carry. So you should remember each vertex carry a parameter lambda, a factor of lambda, which is considered to be small. So downstairs you have 1 plus all the lambda, and we can in the downstairs then we have 1 plus this power series of lambda. And then we can do the Taylor expansion again to bring them to the upstairs. Okay, so remember we did before. So now if you do that, then at the leading order to lambda, then we still just have x1, x2, because this divided by that just x1, x2, and then you have this term. But now we can bring this term to the upstairs, and then this sign changes to minus sign. Okay, so this term can multiply that, and then you get the term like that. Okay, coming from bring this term to upstairs. And then you have this term. Okay. And the rest, they're all of lambda squared. So you can also have this change to minus sign, multiply that, but that will be all the lambda squared. Okay, and since here we already neglected things in lambda square, and here neglected lambda square, and so we don't worry about it. Okay, and if you multiply this, also give you lambda square. Okay, so up to all the lambda and that you have, and then as we discussed before, these 2 cancel. Okay, so in the end, you just have 2 diagrams, just one, and then this one. Okay. Yes?
So for the case with the 2 fields, if you
Yeah.
put your vertex as like 1 solid line, 1 dashed line,
Yeah.
here you can read it as the 2 different particles interacting with each other, or the same species interacting with each other if you read it up down. But you lose
that if you...
Yeah, for here, it doesn't matter. In this case, it doesn't matter how you draw them. You mean if I exchange them?
Yeah.
Yeah, it doesn't matter. Yeah.
But in that picture, you can't read, like...
Yeah. Normally, you cannot view up and down, left and right here does not mean anything. Yeah, the order is not important. But actually, in QFT2, you will encounter situations which these are matrices, and then the order become important. But here they just fail because they commute. So no matter how you order them, it doesn't matter. Yeah, they're just ordinary fields. Yeah. Okay, so this order we just have these two diagrams. Okay. So this is much simpler than we did at the first time. Okay, much simpler than we did at the first time, and the cancellation is much easier. So let me just show you the cancellation in a slightly different way, almost identical, but I write slightly differently. So I can also, alternatively, I can also write as this. I can also write G2. So we look at these two terms. We can just take a common factor out. So the upstairs, the first two terms, I can also write it as this times 1 plus this thing, and then plus this. Okay? And downstairs, I just have, and then plus lambda square. And downstairs, I just have 1 . Okay? So now you can just look at these two. You can directly see actually these two can be cancelled. Okay? To be cancelled. You don't have to worry about this one because when this multiply that, you get higher orders. Okay? And so now you just directly also get from here. Okay, also get from here. Okay. So the reason I'm doing this in these two different ways is that this cancellation is actually not an accident. Okay? So such cancellation, so this is not an accident. This is not an accident. This actually happens to all orders. Okay? This happens to all orders. So you can actually show, okay? Okay, so if I call the upstairs, so now let's call the upstairs to be UN, and this to be U0. Okay. So UN is just the upstairs. Okay, and U0 is the downstairs. Okay, so the UN, by definition, corresponding to sum over all diagrams, all Feynman diagrams, with n external leg, and the U0 by definition is sum of all Feynman diagrams with 0 external legs. Okay, with 0 external legs. So then you can show, okay, you can show in general, which is the Gn is just equal to, as we wrote there, just Un equal to U0. Okay, you can show that this defined to be Un equal to 0 is just given by, you find the order, you can show to all orders, this downstairs can always cancel. Okay, always cancel. So the statement is that this is equal to sum over the ratio all diagrams of an external x but without any vacuum bubbles. Okay? So, okay, so now let me just explain what this means, that without any vacuum bubbles. Okay? So this diagram, is a diagram which contains just a straight propagator times a bubble. Okay, so this diagram contains a vacuum bubble. Okay, it contains a vacuum diagram. And this diagram does not. This diagram is connected itself. Okay, so yeah. Similarly, if, when you go to next order, as we discussed last time, that this diagram. So go to next order times. So this is also a diagram with vacuum bubble because you have this part which does not have any external lag. Okay. So this will not arise. Okay. So when you do the when you calculate the ratio, then this kind of diagram you automatically don't include them. Okay. You just don't need to worry about them. So now when you do the ratio, you can just forget about those diagrams and directly write down those diagrams without vacuum bubbles. Okay, so that just greatly simplify your life. Okay, and yeah, 1 second. So this statement is simply a So if you think a little bit, okay, and then you will see that this cancellation is generic. Actually, will work to all orders. And this thinking process is actually quite instructive. And so this is left as a homework. Okay, you can read the part in Paskin which try to explain this, this cancellation. But that discussion is actually not great. It's not great, that discussion. But you can still read it and get the main idea. And so in homework, so I ask you to show this yourself. Okay, I ask you to show this yourself. It's not difficult. Once you get the idea, it's actually pretty simple to see. Okay, and we'll be illuminating. Okay, yes.
So I'm a bit confused on this cancellation because if you're pulling out an order lambda term,
yeah.
Wouldn't your order lambda squared would now be order lambda?
No, you pull the whole thing together. You pull the whole thing together. Just those terms don't matter at this order. Yeah, they just whatever here. When you cancel them, you cancel the whole thing. Just this term don't matter. If you care only of all the lambda square term, and then you can just directly cancel these two. Yeah. Yeah, you can easily convince yourself. Right. You don't have to do a diagram. Just write something a 1 plus lambda plus some other lambda and 1 plus. Yeah. Anyway, you can just convince yourself that this always happens. Yes.
So this cancellation, does it just come out of the math, or is there like a physical interpretation?
Yeah, there is a physical interpretation. Essentially, just say when you look at So this kind of thing is essentially the come from the normalization of your state. This thing is just pure vacuum process, and just come from normalization of the state. And when you normalize your state, they just should not contribute to your to your correlation functions. Yeah, just roughly it's like that. Other questions? Okay, good. So now let's just put this in practice. Okay, let's put this in practice. Let me just write down the most general all the diagrams for G2, to lambda square order. Okay, so now let's look at G2 to lambda square order. So we have already find the lambda order. So at lambda square order, we already draw a bunch of diagrams last time. Okay, so you only need to keep those which don't include these vacuum bubbles. So that just, yeah, let me just write them down. So including this, including that, and also including which the one I forgot last time, this one. Okay, that's it. Okay, and but remember last time we drew many more diagrams, but you don't need to worry about the others, such as diagrams like this. Okay. Good. So let's do another example for the 4-point function. So now it's become much easier because you have much fewer diagrams to consider. Okay, you have much fewer diagrams to consider. So at the 4-point function level, then you first have your free series terms. Okay, so the free series terms you just have like that. It just contracted with itself. Now we have 4 external points. Okay, so this is come from the free series contribution at the 0th order. And then at the first order, at order lambda, you just have this. So that all 4 different phi's from the vertex are contracted with each of the external phi's. Okay, so this is the first order. And then you can also have a diagram like this. Okay. And you can also have, I will not draw all the diagrams, okay? I will just draw, and you can draw more diagrams like this, but these are not vacuum bubbles. And you can also have diagrams like this. The reason I draw them because you are going to do some of them in your P set. Yeah, there's another diagram like that, etc. Okay, so yeah, let me just draw 2 more. There's still some more diagram you can draw to lambda square order. Okay. But again, you just it's mechanical. Okay, with a little bit patience. There's no mystery here. Okay. So now let me make some remarks here. And let me make some remarks here. First, so the diagram you can see separated into 2 types. So the full GN separated into 2 types. One type is called connected diagrams. So connected diagram just essentially by its name, this corresponding to diagrams which all the external legs, they are connected within a single diagram. Okay, and so this is a connected diagram. No, this is a connected diagram, but this is not. Okay, and this is a connected diagram. This connected diagram, this connected diagram, this is not. Okay, this is also a connected diagram. Okay, and you can also have disconnected diagrams. So disconnected diagrams corresponding to diagrams as here. So your external legs separated into subdiagrams. Okay, they belong to product of subdiagrams. And later you will see that actually later we will argue this is actually not interesting. Okay, only connected diagrams are interesting, but in a few minutes. Okay, so for the moment, let's just to define them. Right. And then yeah, yeah, and emphasize again the external PI general. Okay. So each external line, which you can assign a momentum PI, okay, because from the Fourier transform. Okay, from the Fourier transform. So for example, here you have P1, P2, P3, P4 in momentum space. Each one you can assign a momentum and not momentum general. Okay, can be in principle, can be anything. Okay. Good. Any questions on this? Yes.
A trick to know that you got all of them? Can you count, just to make sure you?
No, there's no trick to make sure you counted all of them. The only trick is patience. Yeah. Yeah, you just eliminate. Yeah, you just try to eliminate all possibilities. Yeah. Yeah, it's a finite number of them. You can always do it. Yes.
Can you use combinatorics count the number of diagrams?
Sorry?
Can you count the number of diagrams with just the number of vertices and external points?
No, there's no. I think there's no general formula tell you at each order how many diagrams you should have. There's no such kind of magic formula. Yeah. Yeah. There's only one formula. There's only one. Yeah, it's not a formula. Just only one trend, which you can show that when you go to nth order. Okay, when you go to mth order, guess there are how many, roughly how many diagrams at mth order? Yes?
M factorial.
That's right, m factorial. So it's quite a lot of them, okay? So once you go to, say, fourth or fifth order, then become a lot. And you can be sure that we will not ask you to eliminate to fourth order in your P set. Yeah, and actually, this growth of the Feynman the growth of the number of Feynman diagram implies something deep. Actually, it implies, it's a side remark. It implies that this perturbation theory in lambda is actually not convergent, because the number of diagrams grow too fast, and so if at mth order become m factorial, then that means the mth order contribution also grow as m factorial, and then that means this power series is actually not convergent. It's only a symptotic series, and but still, for many physical purposes, it's enough. Okay. Good. Any other questions? Because this concludes our discussion of calculating such kind of Feynman correlation functions using for interacting theory. Okay. Yes.
You just said that it's not convergent, but it is asymptotic.
Yeah, it's a symptotic series. Yeah.
What's the distinction between those?
Yeah. Symptotic series is the kind of series which just the higher order terms will be small, smaller and smaller for a while, and then grow again. And so if you don't calculate too high order, actually they become they're actually quite reliable. You can bound the arrows. Yeah, you can bound. So this is the heuristic way to say it. Yeah. Yeah, it's just that when you look at the first few order terms, it still can be reliably, it's a reliable approximation to your true answer. Yeah.
So I guess we started out by setting the interaction term to be phi to the fourth, but like the into action aside, but like in general, like you're going to have some series of terms added to your action. Is that how you would do a general interaction, or how does that?
No, depend on your specific theory, right? So maybe your theory, that is just the, maybe that's just your theory. Yeah.
Like how do you like apply this to like a physical problem? Like how do you know what?
Oh, yeah, in physical problem, in 1 second, we will tell you how to come from here to calculate the scattering amplitude. And when you find the scattering amplitude, then you can measure in experiment, then you try to deduce back the action. Yeah.
And in general, what changes is just like how many edges your vertex has? Is that like for phi to the end, you just add one vertex?
Yeah, that's right.
What if it's like, I don't know, 1 over, like something not analytic? Is that?
Oh, it can happen. As a toy model, you can always write whatever theory you want. But in nature, somehow the series we discovered so far is all polynomial. Yeah. Okay, good. So now, so earlier we mentioned that there's this LSD theorem, which tells you that the scattering amplitude can be obtained from these time-ordered correlation functions. Okay, so now let's go back to this LSD story again. Tell you actually how to obtain scattering amplitude from correlation functions. Okay, from correlation functions. So the basic idea is the following. Okay. So the basic idea is following, is that you take your endpoint function, okay, with any external momentum P1 to Pn, okay, and then take all, so as I emphasized here, each Pi is general, okay, but now suppose you take all momentum, all Pi, okay, to be on shell. So now you consider them to satisfy Pi square equal to minus m square. Okay? So, so in order to get the amplitude, you need to do this step. You take all the external momentum on shell. This is very reasonable to expect, because when we're scattering particles, remember we say the initial particle can be considered as a free particle. Fellow particle can also be considered as free particle. If they are free particle, then their momentum satisfies this on-shell condition. Okay. So in order to relate this to a scattering amplitude, and then we need to take external momentum to be on-shell. Okay. But now, if you look at this, you say there are two possible choices for this equation, because this equation has two solutions. Okay, so for each Pi, so Pi 0 can either be plus minus omega Pi. So we are using the same notation we used before. Okay, so this Pi vector is the spatial part, and then we have omega Pi. Okay, so this omega Pi is just the okay? So you have two possible solutions, okay? So now the rule is the following, okay? Now the rule is following. Take, say let's take P1, say take m of them, okay? We take their we take the negative root. supposed to be, so alpha will be 1 over 2m. And then for the rest, say Pm plus 1. So let's consider the following situation, okay? And then you take the positive root. Okay, so let's consider the following situation. Okay, so let's imagine we take such an endpoint function in momentum space, and then we take all the momentum on shell, but for some of them, we take them to be take the negative root, and some of them we take to be the positive root. And then there's a theorem. Okay, so this is called the LSZ theorem, which is 3-person. Liemann, Semantic, and Zimmermann. So this theorem says, under this limit, okay, under this limit, under this on-shell limit, so you will see why we emphasize we call it on-shell limit. So imagine you don't actually put them to be exactly a momentum. You take the momentum to be approach that, okay? To be approach that, we just emphasize. So in this limit, then you find your momentum space correlation function. Okay, you find your momentum space correlation function approach to the following quantity. In this limit, yeah, so first we write down the expression, and then we will explain what this means. And let me just do it downstairs, sorry. Times. So let me do it downstairs. Times. Plus infinity. Okay. So the statement is the following. And here z just some constant. So we don't need to worry about it. So d is just some constant. And so this is square root z divided by this factor for each external momentum. And this is just the scattering this is the scattering amplitude for m initial particles. Oh, sorry, I forgot the minus sign. It should be minus p1, minus p2 to minus pn. Okay. So this is the scattering amplitude for particles with initial momentum minus p1 to minus pm into particles with final momentum n plus 1 to pn. Okay? So essentially, whether you choose the negative root or the positive root, decide whether you are in the initial state or in the final state. Okay, whether you are in the final state in the scattering amplitude. Okay? So let me just write here. Yeah. So let me just copy this again. So this scattering amplitude, yeah, so this is the, yeah, let me just write here. So this is Pn plus 1, Pn plus infinity minus P1 minus Pm minus infinity. So this is the scattering amplitude from, so this is the scattering amplitude. This is the amplitude for the particle with momentum P1, Pm at t equal to minus infinity, transitioning to the particle to the rest particles at this momentum at t plus infinity. Okay. So so to save the rotation, so again this will. So remember previously we defined so if you remember before we defined this object. This object should also preserve the because of time translation symmetry. This object will also preserves the energy and momentum. So this object is also proportional to. So you can extract out the delta function. And then times a quantity which we called scattering amplitude before, say alpha to beta. Okay, so alpha denotes the initial state. So this is the initial state alpha, and this is the final state beta. Okay. Okay. So now if you plug this expression into here, and then you will find then the delta function will just cancel on both sides. Okay, delta function cancels on both sides, and then you find that this Gn, P1, Pn is just equal to approach this product of the delta functions, or approach this this factor, and then m alpha to beta. Okay. So this is a statement of the LSD theorem. It essentially tell you that such a scattering amplitude just can be obtained from this, okay? And yeah, you multiply those things and then just equal to that. So now you observe these are precisely up to this factor of z. These are precisely just propagators for the external legs. Okay, so now you conclude. Okay, so in other words, so that means that the m alpha beta then corresponding to you just take the g, then you get rid of all the external propagators. Okay, because they just corresponding to the external propagators for each external legs. Okay, just get rid of the external legs. Okay. Here I'm just telling you the theorem, and we are going to we will use it, but of course the derivation is a little bit complicated. Okay. So yeah, so let me just, since this is a little bit, so let me just write it in words. Okay. In words, to obtain the scattering amplitude m to alpha beta is that first you calculate so suppose you have m part, yeah, just you suppose the total number of initial particle and the final particle are n, and then you just first take Gn, first calculate, just take Gn for n particles. Okay, so suppose, and then take Pi on shell, and the initial momentum take the lective root, and in the final momentum you take a positive root, okay, of that equation. Okay, and then the last step, you just truncate all the external propagators. Okay, and then you truncated all the external legs. So that just comes from you need to obtain m, but you need to divide this side by this factor, then up to this factor of z. Okay, this factor z will only give you a constant, which let's not worry about it for now. Okay. Yes. Which is putting ad hoc?
Like, why are you just setting some of them to be negative?
Oh, yeah. That I will explain. First, let me just state the rule. First, you understand the rule. Then I try to make you more comfortable. Okay, with the rule. Yes. Okay. Yeah. Here is just the rule. Okay. Here I'm just explaining. Here is the rule. This is a statement you can prove mathematically. So this is a mathematical statement you can prove. Okay, and then following from this statement, and then here is the rule of to obtain the m alpha beta from the G. Okay, and yeah. So if I want to write it in one sentence. So scattering amplitude just equal to sum over all truncated diagrams with external momentum on shell. Okay, so if I summarize into one sentence, it's just this. Okay. So I would say the only thing unintuitive here is this sign choice. Okay, it's this sign choice. Everything else I think is intuitive. Everything else in the intuitive, you take this green function which contains essentially n external legs, and now you just imagine this n internal legs corresponding to initial and final particles, and then it's very reasonable we make them on shell. Okay, because they are physical particles. And then the only thing which may be unintuitive is that why for the initial momentum we need to take the negative root, but for the final momentum we need to take a positive root. And then the final thing here is just if you imagine when you scatter particles and how they propagate to the scattering does not matter. Okay, so the propagator just essentially tell you this particle how they propagate to the scattering point. Okay, and so this should not matter for the scattering process. And essentially, yeah. So we will explain this at the end. Okay, and but before do that, let's just look at one example. Okay, do you have any questions? Yes.
Just to make sure I understand, when we say truncate, we mean divide Gn by this pi.
You just not include just. Yeah, you will see explicitly. We just don't include all the external propagator. Okay. Yeah. Let me give you an example. Will be clear. So let me just give you an example. So let's consider four particle scattering. Okay. Let's consider. Say, imagine you have some. Yeah. So following the convention here is the minus P1. P2, okay? So you have minus P1 and the minus P2. And then you have P3 and P4, okay? So let's suppose we want to calculate such kind of scattering amplitude, two initial particles with momentum minus P1 and minus P2. You see, when you take this to be the lactive root, then the minus P1 actually have positive energy, okay? So the minus P1 actually have a positive energy. So all of them have positive energy, okay? All of them has positive energy. Okay, so if you want to calculate in this case, and then you just take the G4, P1, P4, okay? And then you just take P1 and P2 to take to be negative root. Yeah, just to save the time, say to take to the lactive root, okay? And then P3, P4 to be the positive roots, okay? With the positive roots. And then you don't, and then let me put the C here, then you truncate, put the T here, then you truncate your external propagator, okay? Then you truncate your external propagator. So what this means, so let's look at the leading order contribution to this. So the leading order contribution to that, we already have the diagram there. So the leading order, so those in the free theory, those processes don't contribute, okay, because those things, there's no interaction here. Particle just propagates, okay? So the lowest diagram is this one. Okay, the lowest diagram is this one. So we just consider that diagram. So that's just leading order, just given by that diagram. Okay? And then you have minus P1, minus P2, and then P3 and P4. Okay? So now, according to our Feynman rule, this vertex just gives you a factor of minus I lambda. So if we want to calculate this green function, then we need to include all these four propagators. Okay? But here it tells us to truncate all the, but all the propagators here are external. So we don't include them. So the answer here is simple, just minus I lambda. Okay, and so the leading order contribution to this four particle scattering is just minus I lambda. Okay, and then you have all the lambda contributions, lambda square contributions. Okay, yes.
Why did we consider the other, like the one where one is just propagating and the other has a loop?
I'm going to mention that. Good. I'm going to. That's a good question. Yeah, I'm going to mention that. Yeah. So again, that one does not correspond to the scattering. Essentially, just corresponding to one particle propagated. Yeah, because there's no interaction between the particles. They factorize. Yeah. So this one involves two particles, then there's an interaction, you go to two other particles. Here, you just one particle straight go to the other particle. So this particle, by definition, has to be the same as this one. This has to be the same. So there's no scattering. Yeah, but I will mention this point separately a little bit later. So another possibility, say if we want to consider the decay of a particle into three other particles. Okay? So a decay of a particle into three other particles. So in this case, then again we take G4. So now we take minus P1, and then P2, P3, P4. And now we take P1, P4. Now we take P1 goes to minus root. P10 is the minus omega. And then P3, 2, 3, 4 take it to be the positive root. Okay? And then that corresponding to this process. Okay? And again, the leading term, the non-trivial term is just this. The leading non-trivial term is this. So now this is minus P1. So now this is P2, P3, P4. Again, the leading order, this is just minus I lambda. Okay? Because you don't need to include external x. Okay? And then, yeah, so this goes on to a single particle decay into three other particles. Okay. Yeah.
In the flying form theory, there's no like conservation law or anything for preventing this, right?
No.
This
Yeah.
is legal, right?
Yeah. So now let me make some remarks. Right. So oh, yeah, I erased this, but yeah, fine. So so the remarks. So first, when we say, yeah, you already asked, when we calculate this to the leading order, we only included the connected diagrams, okay? So the disconnected diagrams, in general, factorize it means that when you have a disconnected diagram, means that your process factorizes into subscattering process of lower orders. Okay? So as we were doing here, so there's one other diagram which corresponding to just this one. Okay, just corresponding to this, you have P1 minus P1, say minus P2, P3, P4. Okay? So you can also have a diagram like this. But in this case, just corresponding to P1 separately go to P3, and P2 separately go to P4. Okay, so that's, nothing really happens. So in general, if you have n-particle scattering, so with some number of initial particles and some number of fellow particles, when you have a disconnected diagram, means that you have means you have a situation like this. You have one diagram with some subset of particles go to some subset of particles, and with another diagram, some set of particles go to some set of particles. Okay, so this involves so this is a 3 to 3 scattering, and then essentially this factorized into 2 to 2 scattering, and then one particle just go to another particle. Okay, and so this can already be understood in terms of low order process. Okay, so normally we don't, so we don't include them. So essentially they already understood. Okay, they already understood. So when we define the scattering amplitude, we don't include them. Okay. So we are only interested in process involving all participating particles. Okay. So we are actually run out of time. So this is first remark. So second remark is that since we truncate all the external lags, okay, we truncate all the external propagators. So this kind of diagram, you have a loop on one of the external propagators. So this diagram don't contribute, okay? Do not contribute. Because this one, after you have truncated the external lags, it's no different from this one. Okay, it's no different from that one. And so you don't have to count this one separately. Okay, so this one just corresponding to, say, when the particle propagates to infinity, somehow there's some other process to happen to this particular particle. So when you truncate the external lags, then you don't include them. Okay, you don't include them. Okay. So that means, so with these two, so it means that the scattering amplitude, okay, so can forget. So essentially can forget anything happening to the external lags, okay? You can have complicated things happen to external lags, but they don't matter. Okay, they don't matter. Okay. So to summarize, the scattering amplitude, when you compute the scattering amplitude, you just sum over, following this definition, you sum over all truncated, means you truncate all the external lags, connected, because we want all particles to participate, and then the external particle on shell. Okay, so this is a simplification compared to calculate the general correlation functions. So I have two other remarks to make, but we don't have time. So one remark contains the choice of this sign, y initial momentum corresponding to negative root, and y this corresponding to positive root, and another remark related to this fact of z. Okay, related to this fact of z, and we will talk about them at the beginning of next lecture. And then after that, then we are done. Okay, then we are done with the general formulation of interacting theory, and now we will be equipped with the power. Essentially, you can calculate any interacting theory, any amplitude using perturbation theory, and then but in order to calculate anything useful, we still have to first learn how to treat fermions, how to treat photons, and then that's what we will do next. So we will start in lecture. Next lecture we'll talk about how to deal with fermions, how to introduce fermions, and after that we talk about how to introduce photons, and then we can talk about QED, how photons interact with electrons, etc. Yeah. Okay, good. Yeah.